Welcome to acid-base equilibrium with Ka, Kw, and Kb and buffers by Wu. There are different types of acid and bases. Whenever there's an acid, there's a base. Arrhenius acids are a substance that ionizes in water and produce H plus ion. Arrhenius bases are a substance that ionize in water and produce an OH ion. Lewis acids are a substance that accept an electron pair, while a Lewis base is the opposite and it donates an electron pair. Bronsted-Lowry acids are a substance that donate an H plus ion, while Bronsted-Lowry base is a substance that accept H plus ion. Conjugate acids are a substance formed when a base gains an H plus ion. Conjugate base are the substance that are formed when a acid loses an H plus ion. As you can see from the examples below, this acid is acting as an acid while the water is acting as a base. As you can see, the acid is donating an H plus to the water, so the water becomes the conjugate acid, while the acid becomes the conjugate base. And same goes for the example below. Strong acid and strong bases dissociate 100% in water, and these are strong acids while these are strong bases. Weak acids and weak bases, they only dissociate in water only a little bit. Polyprotic acids are acids that can donate more than one H plus ion, such as sulfuric and phosphoric acid. Buffers are a solution that with a fairly stable pH that will remain relatively unchanged when an acid or base is added or when DI water is added. As you can see for this example of a polyprotic acid, it has 2 Kas and the overall Ka is H plus. I don't know why that 2 is right there. Wait, hold up. Why is that 2 right there? Oh, whatever. My bad. Titration curves. This is a buffer region. This is a buffer region. This is the equilibrium point. Equilibrium point. My bad. These two are buffer zones, while these are equivalence points, and that's the end point. Half equivalence point are where pH, where this point is, and this point, it's half of the equivalence point. It's always half of the equivalence point. Right here, the half equivalence point would be point S, while the equivalence point is at a pH of 8. And buffer region would be between R and T, right around there. As you can see from this concept chart, homogeneous can be acid or base, and the acid can either be strong or weak, so can the base. And over it tells you that strong can ionize completely while weak can't ionize completely. And from that, you can calculate Ka, Kb, pH, and pOH. Helpful tips. P of anything equals negative log anything. So pH equals negative log of H plus, the concentration of H plus, while pOH equals negative log of negative pOH. 14 equals pH plus pOH, and pKa equals negative log Ka, pKb equals negative log Kb. The Henderson-Hasselbalch equation, the key equation for acid and base equilibrium problems. pH equals pKa plus log of concentration A minus over concentration HA would be the acid, and that would be the conjugate base. And so is the pOH, but instead it would be the base and the conjugate acid. And pKb, not pKa. These are examples of how the helpful tips work. The pH of a 0.1 molar solution of a strong acid, HCl. So we would use pH equals negative log H plus, and then we sub 0.1 in, and we come out with a pH of 1. As for this one, we use pOH, and we come out as 1, but it asks for pH, so we minus that from 14 to get 13. So this right here is just a breakdown of the Henderson-Hasselbalch equation, Ka and Kb. You can stop the video right here if you want to like read it. So examples, the value of Ka for, well, oh god, this question, example question. So you would do Kw equals Ka Kb. Kw equals 1.00 times 10 to the negative 14th equals Ka times Kb. Well, in this situation, Ka would be 1.00 times 10 to the negative second, and after you solve that, Kb equals 1 times 10 to the negative 12th. Mixtures: strong acid plus strong base, strong acid plus strong weak base, weak acid plus strong base, weak acid plus weak base. These are titration curves. As you can see, a strong acid and a strong base, the pH would be close to 7. And a strong acid with a strong base, the pH would be at a low. A weak acid and a strong base, the pH would be over 7. A weak acid and a weak base, you can see that the pH is around 7. Okay, the big FRQ. For A, it asks you for the Kb expression. So it's OH minus and the conjugate acid and the conjugate, while the base is on the bottom. in B, it acts for the KB. So you start with the pH it gives you, you go to POH, go to the concentration of OH, and you that's equal to that, and you put that in an equation with that as the denominator, the base, and you come out with a KB of 4.4 times 10 to the negative 10th. For part C, you do 2 ice boxes, as you can see right here, and you simply solve for KB. It's KB from previous you solved for, and you solve for X, and right here you can neglect X because it's smaller than 0.5, and you find the pH to be 5.24. In part D, it asks for pH at equivalence point, and you do the same, 2 ice boxes, and this time you can find a Ka. You don't have to use the Kb. Well, you have to use the Ka, and you can neglect X because later it shows that it's smaller than 0.5, and you come out with the pH of 2.96.